Okay, in the last lesson we looked at evaluating limits, and we noted that the ones that are both interesting and important are the ones that are of the form 0 over 0, and we have to determine what the limit of such a function is. Let's look at this one today. Notice as x goes to 0, the sine of x will go to 0, and of course the denominator x will go to 0. So you have two things that are both going to 0. Just to remind you, the sine function looks something like this. Roughly. And so as x approaches 0, the sine of x approaches 0. So what's that limit equal to? What's going to happen as we get closer and closer and closer to 0 and take the ratio of those things? As we learned last time, the answer could be anything. It could be 1, it could be 5, it could be infinity, it could be minus infinity, it could be 0, could be no limit. It might get two different answers coming in from two different sides. So anything is possible. There's an actual proof that gives you the answer to this by going through a kind of a geometric constructive proof. And I'm not going to go through use the time to go through it. It takes about 10 or 15 minutes. It's kind of interesting. If you have a calc book or want to check it out online, you can go through and actually see it. What I prefer doing is just giving a kind of a convincing argument of what that limit is and leave it at that. In fact, one convincing argument that you can get is make sure that your calculator is in radian mode, and then just put in small numbers. Put in the sine of 0.1 over 0.1, the sine of 0.01 over 0.01, and let them get smaller and smaller and see what the ratio approaches. Or if you want to, you could graph this thing as well. Go ahead and graph it and see what sine of x over x approaches. So there are a lot of ways to kind of get convinced of what the answer is without actually going through the rigorous proof. But here's the way I like to explain it. Here's your unit circle, remember. This is what we used to define the sine and the cosine. And if this is the angle x and this radius is 1, then recall that this length right here, the sector, is 1 times x. So if this is the unit circle, this length is also x. And this length right here, the y coordinate of this point, is the sine of x. Okay? So here you have the sine of x, and here you have x. So the question is, what happens to those two lengths, the sine of x over x, as x gets smaller and smaller? Let's just see once what happens by doing this. Notice as x becomes smaller, of course both of them become smaller, but not only do they both come smaller, they get closer and closer to the same size, because the curvature in this becomes less pronounced because you have less of an arc there. And I can't go down much less than that, I guess, without the marker becoming too broad. But here is what I want you to notice, that as this x becomes close to 0, that this length and this length really become closer and closer to the same, or even the ratio gets closer and closer to 1. And in fact, that's why if you were to graph the sine of x and you were to compare that to just the line y equals x, look at here. Here's y equal x, and this one is y equal the sine of x. Notice here what happens to the graphs. As you come in here closer and closer to 0, those two things are approaching basically along the same line, and so they get x and sine of x become closer and closer, and so the ratio goes to 1. So that's all I'm going to say. Excuse me. That's all that I'm going to say by way of giving a convincing argument, not a formal proof, but a convincing argument that limit is 1. As I say, you can determine it on your own if you want to go check it out. So we're going to accept that as true then, and we're going to use that. That becomes very important for other proofs as well, for other results. Another important one is what happens to 1 minus the cosine of x over x as x goes to 0. Notice we have the same situation. Cosine of x approaches 1. 1 minus 1 is 0. Here you have 0, 0 over 0. So again, you have 0 over 0. And so again, we could have any possible answer. And so what is the right answer? Well, let's graph these two functions and see what they look like. Cosine, recall, looks like this. Okay? So minus cosine is going to look like, let's see, the negative looks like what? The positive becomes negative and the negative becomes positive. Looks like that, real roughly. That's negative cosine of x. And then if you add 1 to it, it's going to shift it up. So you add 1 to it, and it shifts it up like that. So there's the graph of 1 minus cosine of x, and we want to compare that to the function x. There's the function x right there. Here's y is equal to 1 minus cosine of x. Here's y equal x. Okay? So notice, unlike the sine graph, which we had here earlier, in this case, these two graphs don't come along to 0 kind of along a tangent line. They don't come kind of tangent to each other. And in this case, this graph comes in down deep and low, right? It comes in nice and deep and approaches 0 much faster than this one does. So unlike the x and the sine of x, which look like this, here comparing the two look very different. So let's see what the actual answer is. And I'm going to use the same trick that I taught you last time because it's kind of clever. Remember what the word conjugate means? It means that you multiply both the top and the bottom by the same thing, which is allowable. I haven't changed the function as long as you multiply both the top and the bottom by the same thing. That's just a fancy form of 1. So this limit is equal to the next one. And now I'll use FOIL. And when we use FOIL, we're going to get 1 times 1 is 1. So 1 times 1 is 1. Here you're going to get negative cosine of x. Here you're going to get positive cosine of x. So those two undo each other. And then you have cosine times cosine is cosine squared. 1 minus cosine squared is what you end up with there. And on the bottom, you have that. Well, how does that help? That looks more complicated than what we had before. But we're in luck, because I remember a trig identity. I remember that sine squared x plus cosine squared x is equal to 1. So 1 minus cosine squared x is sine squared. So here's the trig identity, which is useful. And here you have x times 1 plus cosine of x. So now let's go from there and see what happens. This is the limit as x approaches 0. Sine squared is the same as sine times sine, so I'm going to write that as sine of x over x. And I have another sine of x here, divided by 1 plus the cosine of x. And now we're almost done, because what happens? As x goes to 0, what happens to sine of x over x? Aha, we know what happens to it. It approaches 1. So the first thing is going to approach 1. And the second thing, what happens here? The sine of x approaches 0. Cosine of x approaches 1. 1 plus 1 is 2. 0 over 2 is 0. 0 times 1 is 0. So there's our answer. There's our answer to that one. I'm going to erase all this and just put the answer down. 1 minus cosine of x over x is equal to 0. And I show you this problem not only because it shows a clever technique, but it's also going to be very important in just a couple days, maybe a week, and maybe 4 or 5 lessons from now when we look at slopes of functions. So that's an important one. Okay, very good. Here's another important function having to do with trig functions, or I should say important limit. And again, I encourage you, go ahead and use Decimus or use your own calculator or something like that in order to get a graph of this. Before you graph it, see once if you can guess what the graph looks like. Okay, let's think about this. This is the composition of two functions. We're taking x and we're first doing this to x. That's the inner function. And then once we do this to x, then we're taking the sine of it. So it's the composition of two functions. So if you want to, you can kind of think to yourself, here's the function 1 over x. And here's the function sine of x. Okay? So what happens? As x approaches 0, and let's make it even easier by just coming in from the right-hand side. As x approaches 0 from the right, x is getting closer and closer to 0. What happens to 1 over x? 1 over x blows up, right? It's going off to infinity. So this thing here is going off to infinity, getting larger and larger and larger. So this thing in here is getting larger and larger. And what does the sine do when it sees things that get larger and larger and larger? It doesn't care what the actual form of this is. All it knows is that it's seeing things that are just getting larger and larger and larger and going off to infinity. And so what does the sine do? It just keeps going up and down and up and down and up and down and up and down. So if you start someplace here and you head towards 0, let's do it again. 1 over x is going to go off to infinity, get really, really big. And so we're moving in this direction. So 1 over x is going to get really, really big. And as sine sees something that gets really, really big, it's going to just go up and down and up and down. So wherever this thing starts, it's going to just keep going up and down and 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 up and down, and just go crazy like that, always going between a positive 1 and a negative 1. So recall, that's the kind of function that we discussed a day or so ago, or a couple sessions ago, where we said, oh yeah, you can have a function that just keeps oscillating like crazy, never settling down. And so this is an example of a function that has no limit there. Let's say does not exist. Does not exist. I keep using a DE. Maybe I should be going does not exist. Anyway, that's the idea. And so there's no limit. Okay, so that's a rather important one, okay, just because of the strange behavior. The last one that we're going to do is connected to this one. What happens if you take x times the sine of x? What does that graph look like? Well, this is as good a place as any to talk about multiplying functions. We didn't do this too much earlier, but if you recall, if you multiply functions, you take basically this value. For any value of x, you take this value and you multiply it by that value. So here's the way we can sketch the graph of this function. I first just sketched the graph of y equal x. Y equal x just looks like this. Okay, and then you'll see why in a second. I also sketched the graph of the negative, y equals negative x. It's going to look like this. Okay? Now, what does this graph look like? At various values of x, the sine will be 1. Remember how big the sine ever gets? The sine gets up to 1, down to negative 1, and of course hits 0 in between. So the largest this thing ever hits is 1, the smallest it ever gets is negative 1, and then it hits 0 in between. So whenever this value, for whatever value of function this is equal to 1, 1 times x is going to be a point right on this line. Wherever this function hits negative 1 times whatever the x value is going to be on this line. And then whenever this value is 0, the sine of this thing is 0, then of course 0 times anything is 0. So what you basically have is you have this function that we originally had, but the amplitude of it, the rate, the size of it going up and down, varies as you go along the x-axis. So I like to kind of start here, for example, and again it's going to do the same thing as before. It's going to keep wildly oscillating, but now those wild oscillations are getting pushed right in there towards 0. And the same thing if you were to do it on this side, like that. So this limit here, even though it has wild oscillations, it still has the property that, remember what I said a limit, the idea of a limit is? We say that a limit, as this thing approaches A, this is L, we say the limit is L if, here's the key, no matter how small of a little interval I make around there, I can make another little interval around here so that everything in here gets sent in there, with the exception of A itself. We never care what happens to A, we just care what happens around A, okay? So the point is, no matter how small I make this, I can then make this small enough so that everything in here gets sunk in there. And that's certainly true here. If you give me a little interval right there around 0, I can choose a little interval along the x-axis, so everything in the x-axis, the value of the function gets sent in there. If I make this interval a little bit smaller on the y-axis, all I have to do is choose a smaller interval on the x-axis. So the point is it gets squeezed in, unlike this other function where it just keeps oscillating through all the values from 1 to -1, never settling down. If I make a little interval there, there's no way it's going to stay in there. It keeps bouncing all the way around from 1 to -1. Here, I can make it, no matter how small I make it, I can just choose this one small enough so that everything stays inside. So that right there, as the picture shows, is going to 0. So that's a very important limit. That's more important actually if you have any interest in going on into higher calculus and higher levels of mathematics. I won't spend more than just a minute on this, but if you do the same thing with x squared times the sine of 1 over x, then instead of drawing a line, you draw the parabola. So it looks like this, the negative looks like this, and then you multiply that times the sine of x, and it comes in like this too. And this one also has a limit of 0. As I say, you're getting more than you bargained for with this. The difference, this one here, the limit doesn't exist. Here, the limit exists. Here, the limit exists. And also, a key word, this is called differentiable. It's also, the derivative exists at this point. That's a word we're going to learn later on. But if you're familiar with that word, this is better behaved than this one yet. So there you go. Next time we're going to look at limits going to where x goes to infinity. Very good.